Hello students, welcome to the class Heterocyclic compounds. In the last class, we have studied about the synthesis of 5-membered heterocyclics. In this class, we are going to study about structure of 5-membered heterocyclic compounds. The simplest 5-membered heterocyclic compounds are furan, thiophene and pyrrole. So here we are going to study about the structure of these three molecules. To study the structure of any compound, the first thing required is their molecular formula. So the molecular formula of furan is C4H4O, thiophene is C4H4S and pyrrole having molecular formula C4H5N. So these molecular formulas can be obtained by the analytical estimation of elements and then their molecular mass. So molecular formula can be given as C4H4O, C4H4S for thiophene and C4H5N for pyrrole. And the structures, so these molecules can be represented by these following diene structures. They are having a ring structure and oxygen is present in the furan, double bond with two double bonds and one sulfur is present in thiophene, two double bonds and one nitrogen is present in the pyrrole. So one would think that furan having the properties of diene and along with ether because carbon oxygen carbon bond is there. So it can show the properties of ether. Thiophene, it is a diene along with the properties of thio group and pyrrole diene along with the properties of secondary amine. But when we study the properties, these diene structures fail to explain the following properties, means exactly what we thought there should be a diene and along with ether or diene along with thiol group or diene along with secondary amine properties. But these compounds shows different properties, that is they behave like benzene and undergo electrophilic substitution reactions. Behave like benzene means benzene is an aromatic compound. Electrophilic substitution reactions are characteristic reactions of aromatic compounds. So here these three compounds behaves as an aromatic compound and they undergo electrophilic substitution reactions. Unlike secondary amines, pyrrole lacks basic character. So in the secondary amines, NH group is present and nitrogen bears the lone pair of electron. So it donates that lone pair of electron to the proton and it forms a new NH bond by losing the pair of electron, and this is called basic character. But pyrrole, unlike these secondary amines, it will not show this basic characters easily. But by observing the structure, one would think that it should behave as a base. But here pyrrole lacks basic character. Furan, thiophene and pyrrole are flat molecules. By observing the structure, it is not a flat molecule. But here actually they are flat molecules. So to explain that, why the behaviors are like this, so it is explained by molecular orbital picture or molecular orbital structure. So let us see the molecular orbital structure of pyrrole. So in the pyrrole, 4 carbons and 1 nitrogen is there, which forming a 5-membered ring. And this pyrrole all the 4 carbons are sp2 hybridized and nitrogen is also sp2 hybridized. So sp2 hybrid orbitals, hybrid atoms having 3 orbitals, sp2 orbitals. So carbon forms 2 covalent bonds with adjacent carbons and 1 covalent bond with carbon hydrogen. Nitrogen forms 2 covalent bonds with adjacent carbons. So 2 carbon nitrogen bonds, 2 carbon nitrogen covalent bonds and 1 covalent bond with hydrogen. And all these molecules having one pz orbital which is perpendicular to the plane. So here the pz orbitals which bearing single electrons, the carbon pz orbitals bearing single electrons and nitrogen pz orbital having 2 electrons. So total there are 6 pi electrons are present. All the above orbitals are overlapping. Overlapping of all the above orbitals takes place and overlapping of all the below orbitals takes place. So we can represent here all the above orbitals are overlapping, all the below orbitals are overlapping. So they forms electron cloud above and below the molecule. So there is an delocalization of electrons or electron cloud or the pi molecular orbital which having 6 pi electrons. The electron cloud, this is called as electron cloud which having 6 pi electrons. So these electrons are involved in delocalization. The lone pair of electrons of nitrogen are involved in the pi molecular orbital cloud. So they are not freely available for the reaction. They are involved in the pi molecular orbital cloud. So that's why nitrogen is less basic in pyrrole. It can't donate these 2 electrons easily for the proton. So therefore it lacks the basic character here. If these 2 electrons on the nitrogen are easily available, if they are out of the pi molecular orbital cloud, then it would donate it easily. But here the pair of electrons are involved in this pi molecular orbital cloud. They are not free. So, and this is called as molecular orbital picture. This is called molecular orbital picture of pyrrole. So among that 4 carbons and 1 nitrogen forms 3 sigma bonds, 2 with the adjacent carbon, 1 with hydrogen. And this sigma bonds lies on the plane. Pz orbital, unhybridized Pz orbital which is perpendicular to the plane. The Pz orbital of carbon having single electron, Pz orbital of nitrogen having 2 electrons. So all the above orbitals are overlapping, all the below orbitals are overlapping and they forms a pi molecular orbital cloud above and below the orbital. So we can represent the structure like this, but here there is no fixed double bond or the nitrogen is not having a lone pair of electron because all these pi electrons are involved in delocalization. So this is called molecular orbital structure of pyrrole. The pyrrole also shows resonance. So according to resonance theory, pyrrole is considered to be hybrid of the following canonical forms. So this first one, it is not an actual structure of pyrrole. This is not an actual structure of pyrrole. It is just one of the hybrid. So that is called a canonical forms. These all are called as canonical forms. And actual structure of a pyrrole is hybrid of all these canonical forms. So see here in the first structure, lone pair electrons present on the nitrogen are shifted to the adjacent nitrogen carbon bond, and the electrons between these carbon and carbon are shifted to the next carbon. So it gets a negative charge here, negative charge, and double bond on this nitrogen oxygen, nitrogen and carbon, and nitrogen loses the pair of electrons, so it gets a positive charge. Next, these electrons are given to adjacent bond, and next bond electrons are shifted to carbon. So negative charge at this position and new bond is formed here. Again next, these pair of electrons are given to the adjacent bond. These nitrogen carbon bonds are given to the next carbon. So now this carbon having extra electrons. Again the electrons are given to the adjacent bond. That electrons are shifted to carbon. So here this carbon gets the extra electron and here a new bond is formed. So that these all are called as canonical forms. Means the electrons are delocalizing and it forms the different structures, and these structures are called resonance structures. These individual structure is called canonical structure, and actual structure of pyrrole is hybrid of all these structures. So actually it is hybrid equivalent to all these. So we can represent that is hybrid structure as, so hybrid structure, the 5-membered molecule, hydrogen, all the carbon hydrogen bonds are present here and inside one circle, so that there is no any fixed double bonds. So inside one circle, this represent the hybrid of all these canonical forms. So this is also again confirmed by measurement of bond length. This also confirms the hybrid character of a furan. So if the first structure, if this first structure is considered, if we take the diene and nitrogen having a pair of electrons, then this carbon-carbon bond, there is a single bond, so that should be of 1.54 angstrom. These two carbon-carbon double bond should having the bond length 1.34 angstrom. But when the bond lengths are measured, this carbon-carbon double bond is this carbon-carbon bond is 1.43 angstrom. So it is less than the single bond, carbon-carbon single bond. And these two bonds, actually here double bond is there. So when double bond, so one would think that it is 1.34 angstrom, but it is actually 1.37 angstrom. It is more than the actual double bond. Here this is less than actual single bond. So, and the nitrogen carbon bond, it is also 1.38 angstrom. This is less than actual nitrogen carbon single bond. So this bond length confirms there is no pure single bond or no pure double bond, and the furan having a hybrid of all these canonical forms. Therefore, it having a aromatic character, furan having aromatic character because there is an electron delocalization takes place. So that's why instead of addition reaction, it undergo addition reaction, but at the extra conditions when we are providing high pressure, high temperature, then only it undergo addition reaction. But it easily undergo substitution reaction because the carbons are, that is electrophilic substitution reaction, because the carbons are having more electron density. Structure of furan and thiophene. Like the pyrrole, in the furan also 6 pi electrons are present, and in the thiophene also 6 pi electrons, means 4 carbons and 1 oxygen, which will donate the electron. So here also the oxygen that having lone pair of electron in the sp2 orbital and also lone pair of electron in the pz orbital also. So this is pz orbital which having a lone pair of electron is involved in the delocalization. So it involved in the overlapping, all the above orbitals will overlap, all the below orbitals will overlap, and it forms again the molecular cloud above and below the molecules. Thiophene also same, the sp2 orbital also having a pair of electron and pz orbital also having a lone pair of electron. So all these above orbitals overlap, all the below orbitals overlap. So both these furan and thiophene having a pi molecular orbital which having 6 electron, 6 pi electron in the molecular orbital. So these two are called molecular orbitals of furan and thiophene. So let us see here in the pyrrole, if this is the structure, the pi molecular orbital, this is the molecular orbital structure. The pi molecular orbital having 6 pi electrons. The molecule is planar. The actual bonds which are the covalent bonds, that covalent bond containing molecule is a planar and it having a ring structure. So according to Huckel's rule, the molecule should be planar, the molecule having a ring structure, and the molecule which obeys 4n plus 2 pi electrons, and that molecule is called aromatic molecule. If the molecule is aromatic, then it should having a planar structure, ring structure, and it should obey 4n plus 2 pi electrons. So here n is an integer. So here one ring is there. So we can consider n is equal to 1. So 4 plus 2 is equal to 6. So here 6 electrons are there. So which is that obeys the Huckel's rule. So according to that, the molecule is aromatic. Similarly, when we see the structure of furan and thiophene, again the molecular orbital cloud which having 6 pi electrons in the cloud. So the pi molecular orbital having 6 pi electrons. So that is 4n plus 2 is equal to 6. It has a lone pair electron in the p orbital which is perpendicular to the plane. That is unhybridized pz orbital that having lone pair of electron which is involved in the delocalization. In the thiophene also 6 pi electrons are there. So 4n plus 2 is equal to 6. Both the molecules are planar. Both the molecules are ring structures and they obey 4n plus 2 pi rule. Therefore, furan and thiophene are also aromatic compounds. So aromaticity of 5-membered compounds here, which one is more aromatic and less aromatic? We see now according to this molecular orbital theory, all the 3 molecules are aromatic in nature. Let us compare the aromaticity of a 5-membered heterocyclic compounds. So here we have studied now the molecular orbital structure of pyrrole, furan and thiophene. Let us compare the aromaticity of a 5-membered compound of heterocyclic compounds. So from this structure it is explained that they possesses properties of conjugated diene, and along with that ether or a sulfide or amine. But all these 5-membered heterocyclic compounds are aromatic in nature. And according to Haeckel's rule, aromatic compound should be cyclic, it should be planar, and it should have 4n plus 2 5 electrons. So these molecules obey the Haeckel's rule. Therefore, they are aromatic in nature. They show electrophilic substitution reactions, which is a characteristic property of aromatic compounds. The values of heat of combustion shows resonance stabilization to the extent of 20 to 28 kilocalorie per mole. So if heat of combustion is more, then stability of the compound is also more. So when the stability is more, if the compound shows aromatic behavior, then only the stability of the compound is more. So these properties shows the compound is aromatic. Another one is the aromaticity of heterocyclic compounds depends on the 2 electrons which the heteroatom contribute to the pi system. So in the pyrrole also, the nitrogen which is distributing or which is sharing the pi electrons to this molecular orbital cloud. The pyrrole which distributes these electrons to the pi towards the pi molecular orbital cloud. In the furan also, oxygen donates the lone pair of electrons. In the thiophene also same, the sulfur will donate the pair of electrons for the pi molecular orbital cloud. And furan and thiophene having another extra lone pair of electron which is present in sp2 hybrid orbital. Therefore, it is out of the pi system. So, according to that, furan, thiophene and pyrrole, all the 3 molecules are aromatic in nature. Now, let us compare the aromaticity. So, along with the benzene. So, benzene is the most aromatic compound. And then next is the thiophene. Then pyrrole. And last one is, that is least aromatic, is the furan. So these compounds are, the aromaticity is compared depending upon the resonance energy. So what is resonance energy? Resonance energy is the energy, that is the difference between canonical form, energy of canonical forms and energy of the hybrid. If this energy is more, then compound is more stable or more aromatic. So benzene having 151 kilojoules per mole of energy, thiophene having 117 kilojoules, pyrrole having 88 and furan having 71. So among these 4, the furan is least aromatic and benzene is more aromatic. This is because the electronegativity of the atoms. Why they differ? Because in the benzene also, the pi molecular orbital cloud having 6 electrons. All these 3 molecules also having 6 pi electrons in the pi molecular orbital cloud. But why this aromaticity differs? That is because of the electronegativity of these atoms. Sulfur having less electronegativity than this nitrogen and oxygen. So here the paired electrons are donated completely to the pi molecular orbital cloud. But in the nitrogen, it is being a more electronegative, the shared electron are somewhat attracted towards the nitrogen. Therefore, the resonance energy is less. In the furan, it is still more electronegative than the nitrogen. Therefore, the shared electrons are somewhat attracted towards the oxygen. So, there is more electron density in the oxygen, density on the oxygen compared to all the carbons. Therefore, it is having less resonance energy. So this is the order of aromaticity of the heterocyclic compounds. Among these three heterocyclic compounds, thiophene is more aromatic and furan is less aromatic. So this is about the molecular orbital structure and aromaticity of 5-membered heterocyclic compounds. So you may have to explain here the molecular orbital structure of pyrrole, molecular orbital structure of furan, molecular orbital structure of thiophene. I have explained one, that is pyrrole, completely. So like that you have to explain the furan and thiophene. Next is the aromaticity of 5-membered heterocyclic compounds. So you have to compare the aromaticity of all the three heterocyclic compounds. In the next video, we are going to study about electrophilic substitution reactions of these 5-membered heterocyclic compounds. Thank you.